Hello everyone, welcome to my presentation. My name is Guoliang Zhao. I'm going to present our paper predicting performance anomalies in software systems at runtime. I'm very happy to work with my supervisor, Dr. Ying Zhou, Dr. Safar Hassan, Dr. Chung, and Toby Coben on this project. Performance anomalies are unexpected performance degradation that deviates from the normal behaviors of software systems. For example, a user requests web pages from a web server. However, the web server is having insufficient memory space. Then there will be unexpected delay or even crash when the web server tries to send the web pages back to the user. Operators are required to monitor the behaviors of software systems at runtime. Then operators analyze the monitor information of a running application such as execution logs, CPU usage, and memory usage. Then operators will detect anomalies in the application and take corrective actions to correct the application if there is any anomaly. But however, it is challenging to manually track executions of complex and large-scale software. For example, we have software running in a cloud with hundreds of machines. Operators are overwhelmed by the large amount of information that is collected from each machine in the cloud. So prior studies propose approach to detect performance anomalies by analyzing the monitor information, the execution logs, CPU usage of a running application. However, the prior approaches can only detect anomalies after the anomalies have happened. Such limitation causes an inevitable delay in taking corrective actions to prevent the performance anomalies from happening. So to address the limitation of existing studies, we propose our approach about predicting performance anomalies at runtime. We aim to raise warnings of performance anomalies in advance before the occurrences of performance anomalies. First, we train predictive model to predict normal behaviors of software systems. We collect monitoring metrics from normal running instance of software when the software is running normally. Then we collect the monitoring metrics, then we train the model to predict the future monitoring metrics, the monitoring metrics at the future second, using the monitoring metrics collected from the previous seconds. As shown in this slide, we use the monitoring metrics collected from second 1, 2, 3 to predict the monitoring metrics at second 4. We keep doing this. For example, we use the monitoring metrics collected from second 2, 3, 4 to predict monitoring metrics at second 5. But we keep training the model to predict the future monitoring metrics using the previous monitoring metrics. By doing this, the model can be trained to learn the behavior of the system. Since we are trained the model on normal behaviors, then the predictor model will learn the normal behaviors of the system. In our study, we used long short-term memory LSTM neural network as our predictive model because LSTM can capture the time-sensitive dependencies among the monitoring metrics at different seconds. Then we use the trained predictive LSTM to detect early deviations from the normal behaviors. The LSTM will predict the future monitoring metric, for example, the memory usage. Then we have the real observed memory usage of the system. After a memory leak bug starts happening, the real observed memory usage starts to increasing because of the memory leaking. But our LSTM model predicts the normal behavior of the system. So the memory usage will keep on the same level without increasing. As shown on the right of the slide, the difference between the prediction and the real observed memory usage will keep increasing. Then once the difference is above a threshold, our approach will raise an anomaly warning. Say the system is deviating from its normal behavior and there will be a performance anomaly happen in the future. We test our approach on two subject systems, Hadoop MapReduce applications and Elasticsearch. We need to collect monitoring metrics from the normal and anomalous executions of the subject systems to train and evaluate our approach. First, we run the systems with various workloads. For Hadoop MapReduce applications, we input randomly generated text files to them to simulate the workloads. For Elasticsearch, we use the benchmarking test workloads provided by Elasticsearch itself to do the workload simulation. Then, we need to obtain the buggy systems in order to have the anomalous executions of the subject systems. We obtain the buggy systems by injecting bugs into the source code of the subject systems. For Hadoop MapReduce applications, we identify 7 applications to inject bugs. For Elasticsearch, we identify 90 classes for handling HTTP requests to inject bugs. At each bug inject location, we inject 3 different types of performance bugs: CPU infinite loop, memory leak, and deadlock. In total, we have 291 buggy systems. Then we use the RBM Java metrics agent to collect the JVM performance metrics of the subject systems while they are running. We collect 5 categories of monitoring metrics: CPU usage, memory usage, number of threads, number of loaded classes, and time spent in garbage collection. So this is the collected dataset. For the data, for the monitoring metrics collected from the normal executions of the subject systems, we use them as training dataset to train our LSTM neural network. For the data collected from the anomalous executions of the buggy versions of the subject systems, we use them as validation and testing dataset. We compare our approach with 2 existing baselines. The first one is called Supervised and Supervised Behavior Learning Approach, UBL approach. They use self-organization map to capture the behaviors of applications. Then we also compare our approach with a simple baseline that erases anomaly warning if the resource utilization, for example, memory usage, exceeds a selected threshold, exceeds 90%. Then the simple baseline approach will raise an anomaly warning. Here is the performance of our approach and the existing baselines for predicting performance anomalies that are caused by these 3 different types of performance bugs: deadlock, infinite loop, and memory leak. The performance of our approach are highlighted under the red arrows. We can see our approach outperforms the existing baselines in predicting performance anomalies. Overall, our approach achieves 98.3 average precision and 95 point average recall in predicting performance anomalies caused by different types of performance bugs. We also measure the lead time achieved by our approach. The lead time measures the time that our approach can raise a performance anomaly warning before the anomaly happens. Here shows the lead time achieved by our approach for predicting performance anomalies caused by these 3 different types of performance bugs. Overall, our approach achieves lead time varying from 20 to 1400 seconds for predicting performance anomalies. In addition to testing our approach on injected bugs, we also replicate 5 real-world performance bugs to obtain buggy systems and to get the anomalous executions of the bug systems and evaluate our approach for predicting performance anomalies caused by these 5 real-world performance bugs. The performance of our approach and the existing baselines are shown here for predicting performance anomalies caused by real-world bugs. The performance of our approach are highlighted under the red arrows. Overall, our approach outperforms the baselines and achieves 98.3 average precision and 95.7% average recall for predicting anomalies caused by the real-world performance bugs. This is the end of my presentation. Thanks for your listening. If you are interested in our research or if you have any questions, please contact us. Thanks.
Hello, welcome for the live Q&A of the third paper of this session. We are here with Guo Liang, who is the leading author of the paper Predicting Performance Anomalies in Software Systems at Runtime. So we are here waiting for your questions. Please, sorry, we just lost you, Guo Liang. Can you turn on your mic camera again? I think he's having a connection problem.
Hello, could you see me? Could you hear me?
We can hear you, but we cannot see you.
Oh, the camera shows on my side. I don't know.
I also don't know, but at least I don't see you. So okay, so apparently the audience can see you, so no problem. Okay, so here is a question for you. Heng Li congratulates you for the interesting talk, and he asks, how do you determine when a performance anomaly occurs?
Okay, that's a very interesting question. So we test our approach on two systems, right? Elasticsearch and Hadoop applications. So for Elasticsearch, we will identify anomaly by basing checking the time that how long it takes Elasticsearch to reply a user request. So because we keep sending requests to Elasticsearch, and we record how many times it takes to give us the feedback. So we will calculate the average time. If for a time period the average time goes about 300 milliseconds, we set up a threshold. If this time average time goes about this threshold, we will see there's an anomaly. Based on that scenario, user will notice a delay in getting feedback from search. For applications, use them to process test files. And then we have the execution logs. In the execution log, the application will output how many progress they made at a time interval, like every 15 seconds. So we will identify anomaly, see if it stops making progress. So the progress stops at 50% for 1 minute or 5 minutes. So we'll see there's an anomaly. It stops making progress.
Okay, thank you very much.
Yeah.
I hope this is enough
Right.
for as an answer. So we are waiting for more questions, but let me ask one of my questions.
Sure.
So from your model representation in the paper, I see that you have 3 different outputs, right? So you have 3 different kind of features like CPU usage, animation usage, and number of threads. So how does that? How does the model work when you give, for example, runtime behavior of an application? Does it instantly give 3 different predictions? Or, I mean, because it seems to me there are 3 different prediction tasks in a single model. So can you explain a little bit on that?
Yeah, sure. That's an interesting question. So what we do is we use a neural network to do the prediction. And in the output, actually, we predict these 3 values at the same time. So we input all the previous metrics, the monitoring metrics. Then in the output in the prediction, we'll predict 3 values at the same time through the value of CPU usage, memory usage, and number of threads. So basically, this is determined in our architecture network, because in the output layer we just output 3 values, and then in our training we train them to predict 3 values.
Something like a multi-class classification kind of.
Yeah, it's not a classification. We see it's a multitask predict regression.
Yeah, it is 3 different predictions for 3 different features. Okay. Have you tried to, for example, build separate models to give predictions for each of these, like one model for just
That's a very good question. So we thought about it. So what we realized is actually if we do this in different models, it will only slow down the system, slow down our approach. If we can do this with 1 model, we don't need to do this with 3 different models. And what we realize is these 3 metrics actually they are they are also correlated, not only correlated, they are related to each other. So that there will be some relationship or correlation in them. Then once your model can learn to predict one, your model can be learned to predict another one because they are in the same system and they take the same input. Yeah.
We have another question from Heng Li. He asks, what are the actions or suggested actions taken when a performance anomaly is detected? So,
okay, that's a good question. So we see our approach when we predict performance anomaly. Now we stop on prediction now in the paper. So we're able to predict. We think about what would be the very nice next step after the prediction. That's also our plan now. What are we thinking about what we should do? Now we can achieve good accuracy when we predict. So the next step would be how can we help developers or operators to automatically stop the performance anomaly from happening. They will predict there will be performance happening, but how can we help them to stop it from happening? Like, so what would be the purpose that, for example, can tell operator developers this is the wrong part in your system. Look at the memory usage. This is the wrong part. So please take a look at your memory. But then we still need to tell them what's the reason of this memory, of this memory leak. What's the exact reason? Hardware failure, or or if there's a memory bug in your source code. So that's would be a very next step to try to figure out how can we help developers to automatically stop them from happening. Yeah.
Okay, thank you very much. We have another question from Fahad. Would you flag a process as an anomaly if it predicts an anomaly in any one of the 3 predictions? Or do you have a way to combine these predictions into a single value?
Okay, so that's a good question. We would flag up our application as anomaly once it reads anomaly any of these 3 predictions. We do not combine them. So we just use every one of them as an indicator. Once there's one anomaly detected by one indicator, we will see there's an anomaly. So
pretty conservative. Like if any of them gives a flag, you say there is an anomaly.
There's an anomaly, yes. That's why we use the 3. So we can combine them. So yeah.
Okay. So I was also very much surprised to see your performance measures, because with the baselines you compare, you are significantly outperforming. So why do you think this is the case? Like, is it really the success of the model or the features you picked, or is it because you are looking at a time period and then? So which one does help in this in achieving such high performance values?
That's a good question. So I would say we use the same metrics and we collect the same data, and then we input the same data to our approach and baselines. So I would say it's not a data thing. Still, I would think it's because of the architecture of our neural network. We use the double layers of LSTM, long short-term memory neural network layers. We double the layers in our neural network, and it's found by existing studies. When you double these 2 layers together, we stack these 2 layers together, it's very good to capture the time-sensitive information in your data. Because I think about our data, it's like we collect metrics every second. So like the data is a time serial data. So time series data. Then you can capture the time-sensitive information in your data. Say if the information collected this second is somehow related to the metric collected at the next second. If you can capture this information, the hidden time-sensitive information, it will be very helpful for you to predict what will happen in the next second. So I would say it's because of the architecture, because of the neural network that we used, that can give us this good performance.
Yeah, I mean, it performs greatly. So congratulations.
Yeah. Thank you.
Yeah, especially like you are looking at a normal behavior and then predicting that the abnormal behavior is coming. So that's a very useful approach. Thank you very much.
Thank
we
you.
have only a few seconds left. Thank you for joining. If
Thanks
there
for
are
help.
yeah.